Hello everyone, my name is Dr. Gail Iles and I'll be talking to you today about how astronauts are going to survive the journey into space for long-term missions on the Moon and Mars, and what challenges space radiation brings to those missions. Before I begin though, I would like to acknowledge the Boonwurrung people and the Woiwurrung people of the Kulin Nations, and I pay my respects to elders past, present and emerging. In the image here you can see Chingal, the emu in the sky, which is a lovely constellation, slightly different from the ones that we're used to. The Artemis missions will send the first woman and the next man back to the surface of the Moon as early as 2024. We have a lot of work to do to prepare technology, our crew, and our spacecraft if we're going to make that a reality within the next few years. The Artemis missions, just like the Apollo missions, have several phases and several stages that we must accomplish before we can have these new set of astronauts, this new modern crew set foot on the surface of the Moon. So the missions range from sending probes, sending rovers, and sending instruments to the surface of the Moon as scouting missions, to sending the first crew to go and orbit around the Moon, not to land, and to continually test the launches that are required to send these spacecraft to the Moon, and to test out new technologies that we're going to need for a sustainable presence on the Moon. Because this time, we're not just going to the Moon to set foot, walk around, collect samples and come home again. This time, we're going to the Moon to stay. We're looking at setting up permanent bases on the Moon, and we're also looking at setting up a permanent crewed habitat on the Moon. We'll see people living permanently on the Moon in our lifetimes. This is an incredible feat of engineering and science, but we are going to have to work to achieve it. We're going to need new materials, we're going to need new technologies, and we're going to need a robust crew who can cope and survive in this harsh environment for longer than we've survived before. Would it be possible for humans to adapt and to provide their own protection in space? Who knows? What an exciting thought. Certainly, the first explorers are going to go to the Moon, to Mars, and they're going to come back to Earth. But it may not be that far into the future that we see people who are going to live permanently on these places. We're going to have people living on the Moon and on Mars eventually. So how will they adapt? It's not known, of course. What we do know, from a 6-month stay on the space station, people get longer. The bones in the spine just stretch out, and people can gain up to 1 to 3 centimeters in height. I mean, as soon as they get back on Earth, they're back to their normal height. But the body undergoes a lot of changes very quickly. You know, we lose muscle mass, we lose bone density. So what if people are living on the Moon, living on Mars for a number of years? They may go through some changes that can't be reversed. Maybe they'll end up taller. Maybe they'll end up with less muscle strength, but perhaps they'll develop a natural protection against radiation. There are little creatures, tardigrades, have been put out into the harsh vacuum of space, not even onto the Moon or Mars, which does have some gravity at least, but just put out into space, and they survive. There are creatures, locusts and cockroaches can survive in high radiation areas here on Earth. So there's certainly some kind of biological mechanism that does protect us, put into these harsh environments for long enough. Up until now, most of the astronauts who have gone into space have gone into what's called low Earth orbit. The picture here shows the International Space Station, a huge spacecraft, the largest spacecraft we've ever built and engineered. And it's been in space for the last 20 years, and we've had people in space. There's been a permanent crewed presence in space for the past 20 years. What you can see in this image is a spacecraft that is in fact very close to the Earth's surface. Astronauts on board the space station are treated to a continually changing view of the Earth as it rotates beneath them. And you can see the beautiful curvature of the Earth, because the Earth is round. And you can also see that very thin slice of the atmosphere, this tiny little shell of gas that surrounds our planet and keeps us alive. Now, of course, the astronauts and everyone contemplating traveling 400 kilometers directly upwards might feel that that is a long way away. But if we put that into context, it's actually still very close to our surface. Here we have a scale diagram of the Earth and the different orbits that are around it. So if we think about the Earth's radius, it's just over 6,000 kilometers. Then going up to aircraft, which is our first line in the diagram, we're around about 40 kilometers. Then if we look at Sputnik 1, the first artificial satellite that went into orbit, that reached an altitude of 200 kilometers. The International Space Station orbits between 300 and 400 kilometers on average, and then various other satellites and spacecraft become increasingly higher in orbit. But in terms of the overall scale of things, low Earth orbit is very low compared to the size of our Earth. So this area in the image, this blue area, is our low Earth orbit. It's very close to the Earth's surface. Now we can go out further and we can go to a medium Earth orbit, or MEO. That's this green bar that we see here. And if we zoom out, we'll see that that stretches quite a way. This is the same diagram, smaller, still on the same scale. And you can see that a medium Earth orbit spans out quite a way until we get to the high Earth orbit out here. So in terms of satellites that we know about, we've got people down here, very close to the surface. We have our GPS, our global positioning satellites, around about 20,000 kilometers away. And then we have our weather satellites in geostationary orbit out here. So when we think about all of the things that are in orbit around Earth, some of them are very close, some of them are far away. But if we scale out again, we see that compared to the moon, everything is still incredibly close to our planet. So when we think about going to the moon and this Artemis mission that's going to send people out there, they have to travel a very long way. They have to travel 400,000 kilometers, and that's just to the moon. Now, up until now, all of the spacecraft and all of the people in this low Earth orbit have been protected by the Earth's magnetic field. So the Earth is spinning on an axis. It contains a molten core of iron and nickel, and that's moving, it's rotating, and what that does is it generates a magnetic field that stretches an incredibly long way away from the surface of the Earth. And what that does is it generates a shield, and the shield protects us from some very nasty stuff that's coming out of our sun. Our sun gives us life, it gives us light, and it gives us heat, but it also gives us a lot more, and that's not conducive to life. So, if we're going to travel to the moon, how is this magnetic field going to protect us? Well, if we're behind the Earth, we're going to certainly be protected in what's called a magnetotail, the tail behind the magnetosphere, which is protecting us from all of the harmful particles that are being emitted by the sun. The problem comes, of course, when that moon moves around in its orbit and comes out here. When it's close to the sun, there's no more protection. So the astronauts who are going to go to the moon are going to have to take a lot of care, and the mission planners are going to need to take care when sending those humans to the moon to see where we are in the lunar cycle, the solar cycle, and the Earth orbit. Let's look in a bit more detail at the sun. The sun is rotating very fast. The sun is a ball of hydrogen and helium in constant nuclear fusion. There are tremendous amounts of energy being emitted at any moment. There is a constant emission of not just light and heat, but particles called the solar wind. You can see that here in this animation. Particles are constantly being emitted, and they're being received on every world in the solar system. Every now and again, the sun explodes and emits these huge amounts of energy in little pockets, as you saw just then. Sometimes those explosions and storms are accompanied by a bright flash of light. And all of this gives us some terminology when it comes to the sun. So I've spoken about the solar wind, but we also have solar flares, these bright flashes of light. You can see one forming just over here. Bright flashes of light are a solar flare. And then we also have matter that is literally spewed out of the surface of the sun, and this is a coronal mass ejection. This instrument is placed in orbit around the sun, close to the Earth, relatively speaking, and it measures these coronal mass ejections. The sun is hidden behind this shield here, and you can see a coronal mass ejection explodes out of the surface of the sun. So powerful is this explosion that it actually saturates the detectors on this satellite, and it can no longer detect anything. It freezes. And you can see all of those particles saturating the detector, and then it has to reset and continue measuring. So the power and energy that's being emitted from the sun is formidable. So for us back on Earth or on the moon, these effects arrive at different times. A solar flare, which is light and a flash, is traveling at the speed of light. So if a solar flare occurs, we're going to see it in just 8 minutes, the time it takes for light to travel from the sun to the Earth or the moon. Additionally, inside this solar flare, there are some X-rays and some other electromagnetic radiation. A coronal mass ejection, on the other hand, is actually a cloud of particles. So because this is matter, it's going to travel a little bit slower, and it will take between 1 and 3 days for us to feel the effects of that ejection on Earth. So the speed, although it's fast, 250 to 3,000 kilometers per second, it still does need a little time to arrive on Earth. And the effects can be quite catastrophic. Because of the electromagnetic nature of these particles, they are charged, they can affect our GPS satellites, they can affect our navigation satellites, and they can affect our communications satellites. And in fact, a huge solar eruption in 2017 was sufficient to take out the power grid in half of Canada. The effects were catastrophic, and it took days to recover from that outburst from the sun. So if we look now at the magnetic field that protects the Earth, or the magnetosphere, and see the effect of a coronal mass ejection, you can see that that curving section of our magnetic field that provides protection is completely squashed by a coronal mass ejection. The sheer force of that energy is enough to really impact the Earth and cause these major effects, as I described in Canada. Again, if the moon, with our brave astronauts on the surface, is behind here and in our magnetotail, no problem. The moon is protected by the Earth. But if it isn't, and a coronal mass ejection occurs, something we can't predict, then those crew are going to be in trouble. And there's one more to add to the mix. There's also galactic cosmic radiation. As if it wasn't enough what was coming from the sun, there is yet another source of radiation that's going to impact us. Galactic cosmic radiation comes from everywhere. It comes from our solar system, it comes from our galaxy, it comes from other galaxies, it comes from the entire universe. Now, our sun has what's called a heliosphere. Our sun actually, because it also generates a magnetic field, can protect us from this galactic cosmic radiation, but not always. It depends on the activity of the sun, and it depends where it is in its cycle. However, when it comes to designing spacecraft for the protection of astronauts and crew, then we're certainly going to protect them against the galactic cosmic rays as well. Let's watch those galactic cosmic rays come in. They're going to interact with the sun's heliosphere. Most of them are going to be deflected away, but not all. So I keep mentioning the radiation. I keep mentioning the harmful particles. When it comes to a solar flare, the actual particles that are being emitted are protons, electrons, and some high element ions. These are atoms that have actually had the electrons stripped off them. And the problem with all of those particles is they're charged. Protons have a positive charge, electrons have a negative charge. These high Z ions have a positive charge. The coronal mass ejections are also emitting protons and electrons. The galactic cosmic radiation has protons, nucleons, electrons, and it also has a bit of antimatter. As if all that wasn't bad enough, we then have an additional problem. The additional problem is that when the solar flares, the coronal mass ejections, and the galactic cosmic rays impact other materials, they generate secondary radiation. So this brings into the soup of particles neutrons and gamma rays. So when it comes to designing our spacecraft, we have to allow for all of these things, and we have to protect against all of these particles. Here on Earth, those solutions are relatively easy. If we want to protect ourselves against alpha particles or positively charged particles that are traveling reasonably slowly, we can do so with something as thin as paper, or even our own skin. Electrons are a bit smaller, so we need something that's a bit more dense than paper or skin. And aluminium is a good metal for that. Lots of spacecraft are made out of aluminium. If we want to protect against gamma rays, which have a higher penetrating power, then we're going to need a much thicker material. So often lead is used. Lead is found in nuclear facilities around the world and in medical institutions and facilities. Neutrons are particularly tricky because we can't see them and they're very difficult to detect. However, water, which we have a lot of on our planet, is a great shield against neutrons. And the image I've chosen here is the nuclear reactor that's in Sydney, managed by the Australian Nuclear Science and Technology Organisation. And here at the centre there is a uranium core that is constantly undergoing nuclear fission, but the neutrons that are emitted are moderated or slowed down by a pool of water. And it's the hydrogen in water that provides the protection. Hydrogen is a particularly special element when it comes to shielding against neutrons. And so many materials that have high amounts of hydrogen, such as plastics or concrete, are used for shielding here on Earth. The challenge we face with spacecraft and launching anything into space is that launching things requires fuel. Fuel is expensive. And so our spacecraft ideally are going to be as lightweight as possible. That rules out the possibility of using lead, and it certainly rules out the possibility of using concrete, both of which are very heavy. It would just simply cost too much to launch. So the engineers and scientists that are responsible for designing spacecraft have got to come up with the perfect combination of materials that will provide not just a cost-effective launch, but they must also be durable to withstand the rigors of the space environment, but they must also provide a radiation shield. And so you can see the challenge becomes more and more complicated. Here I'm showing a picture of the Columbus Laboratory. It's one of the modules on the International Space Station, and this diagram shows how the structure is split through a kind of sandwich arrangement of materials. So the bumper shield that is facing space, that's this shiny metal surface, is actually a very thin piece of aluminium. What follows next is an air gap. Air is a good protection against radiation. It is a medium through which the particles have to travel, and it will slow them down. Next, there come some materials, Kevlar, epoxy, Nextel. These are the kinds of materials that are found in, say, protective jackets for emergency workers or military. These are materials that are high in hydrogen, but they're also a fabric, so they can be worn and molded around the human body and are flexible so that we can continue working whilst wearing them. And they're used inside the spacecraft walls to provide not just radiation shielding, but also to act as a kind of net in case any meteors or debris actually penetrates the first outer hull. They'll be caught in this fabric net and hopefully not make it through into the pressurized portion of the spacecraft. Next comes another air gap, again slowing these particles down, and then there's a third layer of aluminium, and from then onwards you're inside the spacecraft, and that's where the people live. So you can see at the moment the technology is fairly simple. It's a sandwich of materials. It's using the lightweight aluminium that we know we can launch cost effectively, and we're even using something as basic as air to slow down the particles. Up until now, we've taken materials from Earth and sent them into space. But a lot of work is being done on researching, utilising the resources that are already in space. One of the proposed solutions for a habitat on the moon is to actually use the material on the surface of the moon itself and igloo style build blocks out of what's called the lunar regolith and use those to build habitats. Just make blocks using this shiny silver soil. Another solution is to abandon that altogether and just go and live underground, like we did in our first days on the Earth. We started out living in caves because they provided the natural protection. And in fact, that is a great solution from many elements. There are actually lava tubes under the surface of the moon. And these are being proposed as our first habitats because not only are they going to protect against the rapid temperature changes that are encountered not only in space but on the moon in particular, but it will also provide a radiation shield, a very natural one. We just need to find a way to convert that into being pressurized and safe to live in. So I see a combination of all of these things. I see that we'll perhaps take up some equipment, a bit of machinery with us to the moon. We'll put it in place on the moon, and then we'll start to get a bit of a manufactory going on the moon where we will utilize the surface. And there's some great materials up there. Most of the surface of the moon, or 50% of the surface, is a material called silica, SiO2. We know it as sand or glass here on Earth. So it's actually a very versatile material. So if we had the machinery to convert that into solar panels are made out of silica. Then we've got a power source for when the sun isn't shining on the surface. We can manufacture even 3D printed blocks out of this material. And then if we get our machinery advanced enough, then we can even start smelting the surface, and we can get pure silica, pure alumina, pure even oxygen out. And then we have even a breathable source. So yes, I think we certainly need to look far more to recycling and a circular use of materials once we're out there, because there's a lot of great resources. We really don't want to be launching everything from Earth every time. So in terms of the people inside the spacecraft, they are receiving what's called a radiation dose. And we need to monitor how high that dose gets when those astronauts are working in space. Here, down on the surface of Earth, we are all subject to a radiation dose. It's natural, it's in the rocks around us, it's in the food that we eat. It's a natural occurring phenomenon by the nature of the Earth itself. So typically, we receive a dose of, say, 0.2 millisieverts of radiation in a year. So here we have sea level doses and annual doses. So maybe up to 2 millisieverts per year is what any of us are receiving at any time, and we survive quite fine, no problem. If you're to have a CT scan, you'll get a fair old dose, but that's in one go. And as long as you don't have them every day, you'll be fine. There'll be no problem. Somebody who's a radiation worker, so perhaps somebody who works with an MRI machine in a hospital, or somebody who administers X-rays, they're counted and classed as a radiation worker. So they need to monitor how much radiation they're receiving in their day-to-day work, and that's totaled up over the whole year. Their rate is slightly higher. They're now in the kind of 20 millisievert range. Aircraft pilots and commercial pilots and aircrew, they're all monitored as well, because the higher you go in altitude, the thinner the atmosphere becomes, the less protection there is, and the higher the radiation doses become. So even the astronauts on board the International Space Station, although they're very close to the surface of the Earth in the grand scheme of things, they are still getting a higher dose than we would get down here on Earth. So they're round about the 100 millisievert range. And if we look forward to the days when we'll be traveling to Mars, the doses become very high. Now, in terms of the damage that that's going to do to our bodies, if we look at 6 months average on the ISS, with a dose of about 100 millisieverts, then there is a statistical risk of cancer, and you may even suffer from mild radiation sickness. Now, it is sad, but true, that some of the astronauts who have been to the International Space Station have developed cancer as a result of being on the space station. So if we're going to even contemplate sending people to Mars, we have to be aware of these cancer risks. And in fact, if we look at merely the travel to Mars, before we even set foot on the surface, we have an increased risk of cancer. We are now up in the sievert range, and after 30 days, there is a 10% risk of death. Would you want to take that risk? How much do you want to go to Mars? Well, the Human Research Program of NASA say that this risk is currently unacceptable. So we are not going to be sending people to Mars anytime soon. Perhaps in the year 2035, we'll have developed the technology to cope with this risk and to mitigate it. But at the moment, we simply don't have that technology. So back to our astronauts on the space station. Scientists around the world do radiation modeling on the modules of the space station. They put in radiation detectors and see how much radiation those detectors pick up, both in a simulated sense and a real sense, and then they shield for that radiation accordingly. So the top image here is showing the Zvezda module, one of the first modules that was launched of the space station. This is managed by Roscosmos, the Russian space agency, and it shows how much radiation is impacting on the radiation detector if there's no shielding in place. If additional shielding is put in place, then it reduces the dose that arrives at the detector, and we can protect our astronauts better. And this protection is simply in the form of plastic blocks. So this is polyethylene blocks. Here's an example of a block, and they are simply put into the walls of the spacecraft. So Zvezda has some sleeping quarters, as do other modules on the space station, and they have additional polyethylene shielding, and polyethylene is a plastic. It contains mainly carbon and hydrogen, and that hydrogen is the key element that's going to protect not only from these electrons and protons that are coming in, but also the neutrons that are generated. These blocks of polyethylene, these plastic shields, are what's called passive shielding. When we want to protect people against radiation, then we can either limit the time of the exposure, which is not possible in space, we can limit the distance from the radiation source, again, not possible in space, or we can simply put a barrier between the people and the radiation. And that is really the only solution that's available to us in space. So we're making use of that with what's called passive shielding. The shielding is just simply a block in between the people and the radiation. On top of this passive shielding, we can also ask our crew and our astronauts to wear dosimetry. Dosimeters are little devices that measure radiation. You can see that These two European astronauts are wearing these little blue belts, and on here they have these little dosimeters which are monitoring how much radiation they're picking up. These dosimeters will be returned to Earth, and then scientists will take the data from the dosimeters and see how much radiation the crew received whilst they were in space during their 6-month mission. Now that's all very well once you're inside and behind the passive shield. It's all very well when you're inside the spacecraft, which has all of the materials around you. What happens when you go outside and do a spacewalk? In the clip here, we can see the incredible Canadarm moving an astronaut from one part of the space station to another. And you can see all this astronaut has between him and the harsh radiation environment of space is his spacesuit. Now, the spacesuit has to be fabric so that the astronaut can move and work. It has many, many layers to protect the astronaut against a multitude of hazards in space, but it doesn't necessarily provide that radiation protection that the crew need. So all we do is we limit the amount of time that the crew are outside. A spacewalk lasts for between 6 and 8 hours, and then they'll stay inside. And they'll maybe do 1 or 2 spacewalks during a 6-month mission. But we have to monitor very carefully how much radiation the crew are picking up during one of these spacewalks. The space station itself is providing a little bit of protection. And remember that this space station is still in low Earth orbit, so it is still within the magnetic field of the Earth. So I've mentioned passive shields, but one area of research is called active shielding. This is where we take the principle of the Earth's magnetic field and try to recreate it in a device that could be used to protect spacecraft. Whilst the magnetic field of the Earth isn't actually that strong, it does stretch out a very, very long way. And that's what's giving us our protection against the solar wind and those solar particles. So any mechanical device that we want to make to protect a spacecraft needs to be much smaller when compared to the scale of the Earth. And if we're going to make it smaller, then we've got to make it more powerful to achieve the same effects as our Earth provides for us. The only way we can create a strong enough magnetic field in a small area is with superconducting magnets. These superconducting magnets are proposed to surround the spacecraft and generate this huge magnetic field which will deflect the particles as they come in. So this is an electromagnetic interaction between the magnetic field of the superconductors and these charged particles that are coming in. So the idea is that the solar wind and the galactic cosmic rays travel towards the spacecraft, encounter a very strong magnetic field, and then are deflected away and keep our crew safe. There are many problems with this solution. The problems are that these coils, in order to generate a magnetic field strong enough, have to be massive. Not just massive in weight, but massive in size as well. This is our little spacecraft, and surrounding it is a huge, huge coil. This means it is far too large to be launched, it's far too heavy to be launched cost effectively, and once it's up there, it needs to be maintained, because the only way to get these magnets to be superconducting is with very, very cold liquids or cryogens. Again, these would need to be supplied continuously to keep these coils running. And the whole solution becomes impractical. At RMIT University, within the space physics group, we are looking at not necessarily anything new technology-wise, but rather looking at ways to use the current materials and the existing power on a spacecraft to provide the active shielding that's required to shield against the charged particles. So our solution takes the passive shielding, it combines it with an electromagnetic shield, and then through a unique and novel configuration of those elements provides the shielding that's necessary. So all of the other solutions that have been proposed and simulated are huge. They're just too big, they're too massive. And all of the designs thus far have put the coils around the walls of the spacecraft. That generates a magnetic field in the center of the spacecraft, but that's where the people are. And that's the problem. This magnetic field will damage the cells and the tissues of the humans. So just from that fact alone, it's not a viable solution. So what our solution does is it takes the coils away from the walls in that sense and puts them elsewhere so that the deflection occurs outside the spacecraft and generates a protected void. It's exactly where it needs to be, in the center of the spacecraft. So the people know that as soon as those shields are turned on, they're being protected and they're also not being damaged. We've gone back to the basics. We said, what do we need? What strength field do we need to deflect the particles? And how can we get that field from the spacecraft power alone? The International Space Station, for example, is collecting its power from the sun via its solar panels. And it's not very much. It's around about 150 volts. And of course, all of that power, or the vast majority of it, is going to power the life support systems. It's going to keep the lights on. It's making sure the scientific experiments run. So there isn't really much left over for anything else. So what we're doing is we're devising an electrical engineering solution that takes some of that power, uses spikes in current, that are short bursts of current, that can generate the huge fields necessary in bursts, so they're not permanently on. And what we could do is we could monitor the action of the sun. I said that we had about 1 to 3 days forewarning before a coronal mass ejection. So if we knew that that was coming, what we could do is we could tell our crew, go into this module, which has the additional shielding. We can go all Star Trek style and say, raise shields. We can draw on that huge pulse of current that we're going to draw. We can turn off a few of the scientific experiments for a couple of hours. We can charge up our shields, and our crew can stay in just one of the modules. So we're not going to shield the whole spacecraft, and they stay there in a type of bunker scenario, wait out the storm, and then we can power down our active shield, and then they can get back to work. So back to our challenge of landing the first woman and the next man on the surface of the moon. So we have 3 to 4 years to achieve our goal by 2024. There are a number of phases to this mission, as I mentioned, and the second phase that's involved is to send crew from the Earth, launch them from the surface of the Earth, send them to the moon, do a single orbit around the moon, and then return back to the Earth. So these crew will be spending a matter of days in orbit, in space, traveling before they come back again. In terms of duration, that's short, and their radiation exposure will be manageable. The third stage of Artemis, where we start to put a spacecraft in orbit around the moon, and where we begin to contemplate landing the people on the surface, are going to encounter some additional problems. You can see here the gateway orbit is a highly elliptical orbit, and if you remember the image of the magnetotail, it may be that this orbit, at certain points, that spacecraft is going to be not as well protected as we'd like. So any crew who are in the lunar orbital gateway, in orbit around the moon, will be protected by the spacecraft itself. It's going to be a similar design to the International Space Station, so it will be modular, and we have the benefit and the advantage of the materials and technology that we have today to build this spacecraft. But nevertheless, it's still going to be lightweight metals like aluminium, and it's still going to include this polyethylene. We're very innovative as people, and we don't necessarily need all these grand fancy things to get a working solution. So my approach is, let's put all of the materials on the table that we have. Let's put the power limit on the system that we have, and let's say, well, what can we make from this? Let's not be restricted by any of the, oh, you can't do this, you can't do that, that won't work. Let's just take what we have and let's start building. I mean, at the moment we use polyethylene. I've mentioned this it's a very simple plastic. Well, we could potentially dope that plastic, say with 1% or 2% boron. Boron is a great absorber of certain radiation. So we could give that polyethylene a little upgrade for the next type of spacecraft, but it's not expensive and it's not going to change the mass overly. I then think about the first principles of electromagnetism. To me, it's a simple solution. We've got charged particles coming in. We have the magnetic field around the Earth. Well, let's recreate that. The magnetic field around the Earth isn't very strong. It just stretches a long way. We don't perhaps have that luxury around a spacecraft, but it's the same principle. It's still an electromagnetic field that we want to generate. We just can't do it with a superconductor. So how else can we do it? There's a phenomenon called a Helmholtz coil. If you take a coil of copper wire, just any copper wire, turn it into a coil, and then make a second coil out of the same copper, and you bring them to a particular distance apart, they'll generate a magnetic field in the center. Now, it won't be that strong, but it will still be a magnetic field. So can we perhaps get multiple of these coils, and can we perhaps arrange them in a different way and create the same kind of protection that we have on the Earth? That's what we're working on. There's an additional problem for the crew who are going to set foot on the surface of the moon, a problem I haven't yet told you about, as if all the others weren't problem enough. The people who are going to walk on the moon are walking on a surface which itself is creating yet more radiation. You remember that solar wind I told you about, these charged particles? Those charged particles are emitted, impact the surface of the moon, which has no atmosphere like our Earth does, and it has no magnetic field like our Earth does. And instead, those particles are free to just interact and impact the surface of the moon directly. Those charged particles are then charging the surface of the moon. Those protons are traveling at such high speeds that they're actually creating neutron radiation off the surface. This was something that was not predicted in the Apollo days. Everyone was well aware of the protons and the radiation that the Apollo astronauts were going to receive. But the neutron dose that the Apollo astronauts received was actually coming up from the surface of the moon itself. So we have yet another challenge to solve. So when it comes to people traveling into space, we have to consider many, many factors. If we're going to launch off the surface of the planet in the first place, all of our spacecraft and fuel needs to be as light as possible because of the tremendous forces that are required to overcome the gravity of the Earth. That's just to get us into space in the first place. Once we're in space, we have to deal with encountering lots of objects. When spacecraft are launched, they eject pieces of their manifold, they eject rocket boosters, and these either fall back down to Earth or remain in orbit and comprise a lot of the debris that is encountered. So our spacecraft have to be robust, and they have to be able to withstand impacts from debris and other objects. If we're going to go to the moon 400,000 kilometers away, then we need a huge amount of fuel. The rocket needs to be ginormous. The Saturn V rocket launched astronauts to the moon in the Apollo days. But those rockets have become superseded by the SLS rockets, and even Starship has now been contracted to send the next people to the moon. We are going to achieve this, and we know we can. We've done it before. But there is a lot of talk about going further than the moon, and putting people on the surface of Mars. I hope that through the lecture I've given today, you can see that these are not just fuel-related challenges. These are not just about the physiological effects of being in reduced gravity for long periods of time. Our astronauts simply are not going to be able to survive the radiation environment unless we come up with new solutions to shield them and protect them from all those myriad effects that are found in space. We've got the solar wind, we've got solar flares, we've got coronal mass ejections, which are unpredictable and happen at any time. There's the galactic cosmic rays. All of these things are impacting our spacecraft, and they're generating secondary radiation. They're generating neutrons and gamma rays, all of which are going to damage us. And then, as if that weren't enough, when we travel to these other worlds, Moon and Mars, that don't have the luxury of a magnetic field or an atmosphere, our crew and our astronauts, as they set foot on the surface of these worlds, they're going to encounter yet another form of radiation as those high energetic particles are impacting the surface and creating an additional field of neutrons. So it is most certainly in our interest to send probes and rovers and other spacecraft to these hostile environments first, and we'll let them be our guides. We will let those spacecraft advise us as to the environment that our people are going to enter, and we'll take that data and we'll take that knowledge and with it form the best solutions that we can to protect our astronauts and our crew in the future. So I lay down the challenge to all the scientists and technologists and computer scientists and anyone who is involved in material science or technology solutions. Join our quest to develop these materials, to develop these technological solutions, and let's put people on the surface of Mars. Why not? And when following and pursuing your dreams, my advice is to shoot for the moon. Because even if you miss, you'll land amongst the stars. There's always somebody who says, oh, shouldn't we solve the problems on Earth first? That statement implies that we can only have one or the other. We can either fix the problems on Earth or we can go to space, but we can't do both. It also totally bypasses that feeding everybody on the planet is a social problem, whereas space exploration is it's scientific and it's technological, but it's also a fundamental human drive and desire. We are curious people. And we have this incredible situation right now where we can explore space. So let's do it. Let's explore. And we are doing things to fix starvation on Earth. We are working on that. And we're also working to stop climate change and all of these other things, but those are separate problems. Those are social problems, and space exploration is separate. And it's something we can do alongside fixing those problems. And so many technological solutions have come out of spaceflight. You know, baby milk, powdered milk came from space exploration. The packaging food into freeze-drying food came out of space exploration. So many technologies. The cameras in our smartphones came from the Apollo program. There are so many technological solutions that we have on Earth and we utilize daily for the betterment of society that save lives for society because we dared to dream, because we dared to explore. We can do both.